So our next speaker is going to be Dr. Geoff Landis, who was a founding member of the Mars Society, is a noted science fiction author, and is a scientist and engineer at NASA Glenn Research Center. He participated in, I think, the Pathfinder mission. Which one did you put the thing on the solar panel?
That was Pathfinder.
Yes, the Pathfinder mission.
I'll talk about that.
Okay, good. And other things, and has been an innovator with many unique concepts, advanced propulsion, ISRU, you name it. Very creative thinker, he's a great guy, Geoff Landis.
Good morning. So the other day I was on the science fiction panel talking about part of my several lives, and now I'm going to move in and talk about a little bit of science and engineering, talk about Mars oxygen for sample return. And I think actually this may be the one audience where I don't have to explain why that's a great idea. But we'll talk a little bit about myself just to start with. I actually started out as a photovoltaic scientist. I'm a physicist. So in the beginning of my career, I was designing, developing, and inventing solar cells. But when I went to NASA, of course, NASA is very interested in solar energy. In fact, a lot of the innovations in solar power came from NASA, because when you're out in space, every mission needs power. You need it for life support, you need it for communications, you need it for everything. And it's an awfully long way to run an extension cord. So most missions use solar cells. A handful have used isotope power systems, and 1 or 2 missions have actually used nuclear reactors. But by and large, space missions, NASA and commercial, use photovoltaic power cells. So I moved on from there actually to studying solar power on Mars. NASA is interested in putting solar cells in environments where people on Earth have never thought to put them. So my study was looking at the effect of the dusty Martian atmosphere on solar cells. So I became, after doing the analysis, I became part of this team, the Pathfinder team. I was a member of the Sojourner rover engineering team and then the science team. And in fact, here we are. So successful solar power on Mars. There we go. So there's the little solar-powered rover pressed up against actually my favorite rock on Mars, Yogi. Ask me about Yogi sometime. But what I really need to do is point out my favorite part of this mission, which is that little corner of the Sojourner rover, because that was my corner. That had my experiment. As I said, I was looking at the effect of dust in the Martian atmosphere on solar arrays. Of course, the Martian atmosphere is dusty, and we started worrying, well, what if that dust in the atmosphere filters down and lands on my nice, clean, shiny solar arrays? What will happen? So my experiment measured the dust deposition on the solar array as a function of time. And the great thing is the prediction, the theoretical prediction, was 0.25% degradation per day, and we measured 0.28%. And I said, wow, what a great proof of my prediction. Turns out that was an utter coincidence, because the factors that I got wrong by a factor of 2 one way were exactly balanced by the factors I got wrong by a factor of 2 a different way. And it came out that by coincidence, the prediction matched the experimental result. I moved on from that to this mission, the Mars Exploration Rovers mission. A great mission still going on. We are operating the Opportunity rover today. Well, actually, no, we're not operating on Sunday. But Monday we'll be operating the Opportunity rover on Mars. Great mission. I'd like to talk in more detail about that one, but I'm going to have to talk very quickly to get through my slides anyway, so I shan't do it this time. But just one thought about in situ materials in space. This is one conference where people are talking beyond the first landing on Mars, but actually making things, building things, colonizing Mars, living on Mars. We're going to have to build things on Mars. One thing people talk about is building material, but I'd like to point out that Mars actually is one of the great places because building materials lie around sitting on the surface. Here's a chunk of nickel iron that weighs more than a ton that we just happened to drive by because it was sitting less than a mile from our landing site. So here's a chunk of nickel iron that anybody could go and pick up. So if you want to build stuff on Mars, wow. Now here's an interesting question. This is a 1-ton meteorite. How the heck did it get through the atmosphere of Mars, land on the surface, and not blow itself into oblivion? So that's a tricky question on modeling the atmosphere and entry dynamics of Mars. Anyway, this is the mission we want to do, or at least the first of the many missions we want to do. We want to send humans to Mars. Well, in situ resource utilization, and I'll probably slip into using the term ISRU, because in the aerospace industry in general, and in NASA in particular, we have a great fondness for acronyms. I hate acronyms, but I use them anyway. So when I say ISRU, that means in situ resource utilization. Use the stuff that's there. We have actually the world's greatest advocate for that sitting right here watching, so I don't need to convince you of why it's necessary. But the most important thing we need to start with rocket propellant, and rocket propellant is mostly oxygen by mass. However, engineers are risk averse. Engineers do not want to send new stuff on their missions. In fact, engineers have a motto. Their motto is, new technology, that is great, but not on my mission. Everybody wants somebody else to fly it first. This is a serious problem. It leads to something in technology development that we call the valley of death, where people develop technology, it's really great in the lab, they say, okay, now we just need to fly it, and you can't get anybody to fly it. I have a lot of sympathy for the engineers when they say that, actually, because I've been on the other end trying to get flight hardware flying for missions. And when you're doing engineering for a mission, one thing you know for certain is that there are 10,000 failure modes out there that are waiting to get you, and you don't know what they are, but anything that is new probably has a lot of failure modes that you don't even know about. So I have sympathy. On the one hand, I'm a speculative thinker. I want new technology out there. On the other hand, as an engineer making hardware, I want it to work. I want everything to have been demonstrated on somebody else's mission. Moving off a little bit, after the Pathfinder mission, I was involved with this mission, and I should give a lot of credit to Dave Kaplan of NASA Johnson, who came up with this idea that we need to demonstrate fuel production on Mars before we can get anybody to fly it. So this is actually an acronym within an acronym. It's called MIP. That stands for Mars In Situ Propellant Production, Mars ISPP Precursor Experiment. But there it is. Our object was to make a little box, about the size of a shoebox, that would demonstrate that we could make oxygen on Mars from the Mars atmosphere. And there is sort of me and our little team at NASA, Glenn, a little bit younger version of me, but I guess still sort of recognizable. And we designed, built, and flew this. It made oxygen with this reaction. We take carbon dioxide, we electrolyze it, the same way you electrolyze water to make hydrogen and oxygen, and it turns into carbon monoxide, which we're not interested in, and oxygen. Actually, really simple product, actually no moving parts except possibly the compressor to compress the atmosphere, less than 1/10 of Earth's atmosphere. Simple, no moving parts, easy to do, demonstrated on Earth. It's used in solid oxide fuel cells. In fact, the person who worked with us to make the solid oxide electrolysis unit, K.R. Sridhar, after this project, he went on to found his own company, an energy company, to make these, to work with the energy industry as a buffer for power plants. So there we are. There is our flight hardware, designed, built, tested, ready to flight. and we were going to fly it on this mission, the Mars 2001 Surveyor Lander mission. All of you remember this mission, 2001 Surveyor Lander? The 2001 Surveyor Lander was identical spacecraft to this one, the Mars Polar Lander. It was supposed to be, Mars Polar Lander was the first of 5 spacecraft, all identical, all the cheapest Mars spacecraft ever built. And unfortunately, it had a little bit of a problem. December 99, it failed to land. January 2000, they canceled our mission. So I have a little shirt, actually, that says, "My spacecraft went to Mars," and all I got was this lousy T-shirt, because they eventually resurrected the spacecraft when they figured out what the problem was. They said, "Hey, anybody want this spacecraft? You can fly it to Mars for us." A different team picked it up, flew it to Mars as the Phoenix lander, but they didn't fly our experiment. So Mars in situ propellant should have been demonstrated in 2001 if our spacecraft had been there for us. It didn't. So actually, that's one of the reasons why I'm very sympathetic for the engineers saying, "I want to get rid of every possible risk because something is there to bite us." Well, something was there to bite them. 20 years later, we were canceled in 2000. 2020, NASA is going to be flying this mission, the Mars 2020 rover. The rover itself is a copy of Curiosity with a couple of upgrades. But the experiments on it are a totally new set of experiment packages. But the important one, in my opinion, is this one, MOXIE, the Mars Oxygen In Situ Generation Experiment. So 20 years later, and I'm not part of the team, but at last we're going to Mars with oxygen generation. A bit more sophisticated. I actually love their little system if they can get everything to work. They'll be generating about a little bit over 20 grams of oxygen if it reaches full capacity. May not. Here's what it looks like, all of the little systems inside. Oops. Actually, the working element of it is this little part over here, the oxygen generation, SOXE, another nice acronym, solid oxygen, I don't know what the E is, experiment. All of the rest is pulling in the atmosphere, filtering it, getting it ready to go. So with luck, assuming that the great Martian monster does not shoot us down, we will show that oxygen generation and liquefaction on Mars in 2020. Well, let us shift gears entirely. The Mars science goal, the number 1 list for scientists on what they want is a sample return from Mars. It is a priority for science because we can do better science on the Earth than we do in the small experiment sets on Mars. It's also, I will argue, a critical footstep on the way to a human mission, because if we're sending humans to Mars, despite the advocates for one-way missions, probably we want to send them back. Most people who come to Mars would like to actually come back. So we're going to need to demonstrate that we can launch from Mars and return to Earth. So Mars sample return will do both. It'll do this great science. It will demonstrate we can launch from Mars, return back from Earth. And all of those engineers who say, "Man, I don't want this new technology, Mars return, on my vehicle," well, okay, they'll be happy. They say, "Oh, it's been done. Solved problem. We can use that." So here's a view one view of what a Mars sample return mission might look like. The current architecture looks like this. We have a rover that acquires samples. That's one mission. We have a second mission, a Mars Ascent Vehicle, or MAV, that picks up the samples, launches them into orbit. Then we have yet another mission, a third mission, that rendezvous with those samples sent into orbit and takes them back. So this is actually relatively similar to the Apollo architecture, where we launched the people from the moon, but they didn't go directly from the moon home. They went to rendezvous with their Earth return vehicle in lunar orbit, and then that part, the command and service module, took them home. We were not part of the team that was putting this architecture together. However, we tried to do an engineering study of the Mars Ascent Vehicle. We did the engineering study of the Ascent Vehicle. So we needed to do a detailed trade-off study Why? Because if we can use one technology, if we can show that ISRU works for both sample return and human missions, we go down the learning curve. So we need to answer the question, in order for NASA to buy off on this, what does in situ resource utilization buy us? And I will argue we want to do ISRU for the first sample return mission, because we have to fight that mindset. It's too risky for the first sample return. We'll do the first sample return with throwing some technology together with solid rockets and save the ISRU for a later one. But I know engineers. Once you've demonstrated a technique that works, no matter how inefficient and clunky it is, they will keep using that one because they'll say, oh no, this other one is new technology, not on my mission. So we want ISRU for the first mission. Okay, here's what we want, fuel generation. We said there's a lot of different ways to do it. Methane oxygen has a lot of advantages. It's a better propellant. You can make actually more of it from the Mars resources. The oxygen generation I was talking about generates just the oxygen. A difficulty is you have to bring hydrogen. Hydrogen's hard to work with. You have to bring it. Ultimately, when we have humans, that's not too much of a problem because there's plenty of ice on Mars. We can dig up ice. We'll probably have to purify it. We can electrolyze it. We can get hydrogen from Mars. But on the first mission, that is actually really tough. So we picked the second technology for several reasons. But the main part is it will be demonstrated on Mars in the Mars 2020. So we will have it ready to go. So the engineer part of me now says, demonstrated technology. Yes, I want that demonstrated technology. So we picked this one for the generator. The reason is production rate of that MOXIE system, if it reaches full production, it may not. They're still working on trying to hit 22 grams an hour. I'm not sure if they can. But if they did that, 20 grams per hour is actually the bottom line of our study. That's what we need for sample return from Mars. So we picked a hybrid propulsion. We have a polymer fuel, Mars-generated oxygen. So the question is, what's the time required for that oxygen production? Can we do it before we need to come back from Mars? I won't talk too much about the concept of operations, but we land using a sky crane. We generate oxygen. We have set aside up to 120 days for a dust storm if there is one. Then we elevate it, launch the Mars Ascent Vehicle to Mars. An important feature that I would like to emphasize, again, the sort of engineering brain, is something called mass growth allotment. Something that has been discovered on bitter experience is that when you make an engineering design, between phase A, when you come up with the concept, and when you're ready for flight, it gets heavier. And the engineers who do the design say, no, we've accounted for everything, we know what it will weigh, but experience tells us it always gets heavier. So in all of our design studies, we include a mandatory 30% growth allotment. So whatever it is that you can send to Mars, whatever your landing capability is, you need a system landing on Mars that is 30% less than that, because you know that during the manufacturing and development, things that you didn't account for will end up making everything heavier. So those of you who are maybe students doing engineering designs, keep math growth allowance in mind. Your system, the real world systems, are always heavier than the beautiful SolidWorks designs that I show you. So we included that 30% mass growth allowance. There is our system. So look at the system summary. This is all the stuff that is inside. You probably don't need every part of that talked about. We did a lot of trade studies, this versus that versus the other. The other trade study I'm not going to mention is this is not our first Mars Ascent Vehicle study. This is our fifth. So we are comparing this Mars ascent vehicle to other options, solid fuels, liquid fuels, sort of experimental new types of liquid fuels that usually blow up in the lab but might work on Mars. We've done a number of these designs, and part of the key is we use exactly the same assumptions in all of the designs so that we can compare one to another. Power is the big thing, of course. Maybe I just think that because I'm a power scientist. But in situ resource utilization, making propellant, is basically taking energy from wherever you take energy and fixing it into chemical form so you can launch it from Mars. So ISRU really just is a way of capturing energy. Here is the array that we ended up picking, the Megaflex array. There it is being tested in the giant vacuum chamber at NASA Glenn, although it's not under vacuum at this point. Here's the larger of the Megaflex arrays. You can see how large it is. If you look in the corner, there's somebody standing by it for scale. We're using a slightly smaller version of that. And actually, we did look at the wind loads on it. Turns out that unlike Andy Weir's interesting novel, windstorms on Mars do not blow over large rocket ships. They're kind of gentle because of the thin atmosphere. So here is our design. There's the rover, there's the solar arrays, which are getting the power. Engine performance won't go into it too much, but another thing to note, important, is that this is the theoretical performance of the engine. This is the performance that we actually used, because real-world engines do not meet theoretical performance limits. Real-world engines, same way that real-world engineering is heavier than theoretical engineering, real-world rocket engines are not as good as theoretical rocket engines. O to F is the ratio of oxidizer to fuel. We get best specific impulse over here. We get best performance. But we want to run oxygen-rich, because oxygen we don't have to carry to Mars because we make it there. So we will take a little bit of a performance hit and move it off to more oxygen, which means less fuel brought from Earth. Again, several different designs. Actually, all three of the designs worked. Turned out we didn't have to analyze three. They all worked pretty well. There's our Mars ascent vehicle. This is the bottom line. I left out actually about 20 slides with all of the details. But this is the SolidWorks showing it sort of put together. This little box in here is actually the space for the rover to go pick up the sample. We didn't design the rover. There it is, erected for launch. Here's the size. I'm running through these very quickly because I'm out of time almost. But here's how we land on Mars. Skycrane has been demonstrated. Skycrane can land 910 kilograms on Mars. We note the JPL engineers say, oh, we can probably do better than this. But that's margin for us, is that they can do better. We're assuming what has been demonstrated on Mars, 910 kilograms. That was our design limit. So it lands like this. It hovers in the air, and it lowers down the payload. In our case, the payload is not a rover. The payload is the Mars return vehicle. Bottom line is 910. Here is everything folded up to fit inside that Skycrane, carefully putting the cutouts for all the rocket engines, etc. And here is actually the whole bottom line for the system, all of the parts. This is the most important part, 908.9 kilograms. Come on, give me the, out of 910. So we made it, but with not very much to spare. But this is interesting because, as I said, this is the 5th design we've done. It's the first one that fit in Skycrane. The other ones did not fit, or at least they didn't fit with our requirement of a 30% margin. So we can do this with ISRU, making propellant on Mars, fitting inside the existing landing system for Mars. This is the mission that we really want to do. And this is the mission that needs ISRU, because it needs the ISRU to make the propellant on Mars, to lift off from Mars, get back into orbit, rendezvous with the Earth return vehicle, and land safely on Earth. So I think they're saying wrap it up. So let me get to conclusions. Conclusion is our study showed that either a single or two-stage Mars ascent vehicle can use ISRU to meet the requirements to launch the 5-kilogram sample capsule using technologies that we have demonstrated or will have demonstrated by 2020, using a landing system that's demonstrated, and it works better than the mission that does not use ISRU propellant. Those did not close. We couldn't get it to fit inside the landing shell. So the ultimate conclusion is that ISRU, in situ resource utilization, can pave the way for human exploration with a mission that not only demonstrates the propellant production, but can accomplish real science that the scientists, the engineers, and the human team all want to happen. So thank you.
Is this on? Quick question, sir.
You can see where the question is.
You can produce 20 grams of oxygen per hour, correct?
Mm-hmm.
I've been wondering, how do you compress the oxygen into a liquid oxygen form? I assume that's what you're going to use with your hybrid engine? Yeah,
Moxie uses a cryocooler. So actually, when you look at the interior of cryo, only a small part of it is actually producing oxygen. A big part of it is the cryocooler to liquefy it. And that is a big problem, liquefying it and keeping it. Moxie does not store very much liquid oxygen. We can't put kilograms of oxygen into it. It's built to be in the rover and rove around. But it does liquefy it.
Thank you, sir.
Okay.
Do you know if anyone is working on a device to produce feedstock for 3D printers from Martian resources? And do you think that's something that is feasible without building huge chemical factories on Mars?
I would have to think about whether it's feasible. To my knowledge, there's some student teams that have been sort of kicking over the idea, but I've never seen anybody actually work on that. Actually, the stuff that Bob Zubrin works on is probably a better ISRU precursor for that, because he makes hydrocarbons from which you can make polymers, from which you could make 3D printers. Oh, there he is. Yeah, Bob, tell us about it.
I'll just add, we actually are working on exactly that right now. Using carbon monoxide, you can reduce iron oxide to iron and steel, which can be used in 3D printers. So in addition to making plastics which can be used to 3D print plastic parts, steel can be used for 3D printing. And in fact, at my company, we've 3D printed a complete steel injector system for a micro-rocket, bipropellant micro-rocket. So yes, the carbon monoxide that is produced by this process is not merely wasted, it's a powerful reductant that can be used to produce steel.
One last question over here.
Mars Homestead Project. In the Mars Homestead Project, they've been working on that quite a bit. If Frank Kratzman is here, but he has a full plan on how to produce quite a bit of from methane up to greases and epoxies and other resins. Yes, it's been done. Also, your crane to lift it up, if you lift it before you fill it, you can get a much higher crane, or much higher, much lighter crane, because that's quite a ways up away from the crane, so you're going to anyway. Sorry.
Yeah. Actually, good point. We didn't analyze every possible trade-off, and I don't think that was one that we did analyze. So. Okay. One last question, I guess, over here. Final question. Oh, there. Oh. Have we talked about commercializing the solar array, was the question?
Yes, commercializing solar arrays for portability, usability off-gridders.
Yeah. Solar technology for space diverged from solar technology for Earth in the late 1980s, when the solar technology for space moved on to very high efficiency at a relatively high price, where solar technology for Earth went for low costs. So probably some variants of this might be useful for Earth. The particular one we use is awfully flappy in the atmosphere. It wouldn't take high winds. Solar arrays for Earth are rated for hurricanes, but we will see about that. Whereas this wouldn't even take a mild thunderstorm. They're very flappy. So.
Will what's left behind continue to produce oxygen after the return vehicle launches?
I suppose it could. There's no reason to. We didn't design it particularly to last after the launch, and we didn't even look at the question of what does the launch do to things like the solar arrays. So that wasn't a design criteria for it to survive past the launch. But it could be future. Of course, we just launched the tank into orbit, so we could make oxygen, but we don't any longer have a place to store it. So. Okay.
I'm curious why the architecture to have this ascent vehicle to orbit and then wait presumably an entire additional launch window to bring that back. Can that not be done in one mission to have the return vehicle capture that? And then just a quick observation, because you'll know this. I saw a wonderful demonstration at Swamp Works at KSC where they popped dust off of solar panels in like a millisecond.
Yeah, that would be Carlos Caya's work with the electrostatic repulsion on dust. And we have a lot of interest in various technologies for dust mitigation, which I really won't go into. Yeah, there's other possible architectures. We don't actually launch into orbit and then wait for the return vehicle, another launch window. The return vehicle launches while we're still making propellant. So it will be approaching Mars at the same time that we launch. But you're right, there's a lot of different architectural trades, which we didn't do. We were purely doing the engineering trades for a pretty well-defined mission. There's probably more clever ways to do it. There's even the possibility that you could do a direct-to-Earth launch using ISRU, something that would be very hard to do without ISRU because it takes a lot of propellant for direct-to-Earth. So that's another architectural trade. I would love to do that. It would probably be something that would be one fewer mission, which means cheaper. You don't have to have that vehicle that picks it up and takes it back. That's needed only because we were minimizing what's the minimum Mars ascent vehicle. On the other hand, the direct-to-Earth, we'd probably need more landing capability than the sky crane. On the other hand, if you listened to Bob Zubrin yesterday, he's pointing out we desperately need more landing capability on Mars. That is a high priority. So all of these architectural trades are interesting. We need to find the right one, but I can't do them all at once. So.
All right.
Okay, thank you.
All right.